Have you ever wondered how the smallest and most invisible forces govern our day-to-day lives?
People live their days without recognizing forces. However, they affect everyday lives from driving a car to hitting a tennis ball. These everyday actions are often overlooked.
In this video, we will cover the intricate nature of forces and dive into topics like Newton's three laws of motion, operations with vectors, different types of motion, and much more.
To represent a variety of forces, we can delve into the workings of a popular sport, tennis.
In tennis, each time a racket collides with the ball, there are several forces exerted on both objects. Now, we will take a deep dive into the forces of the tennis ball.
Before we explore the intricate details of forces, it is tremendously useful to create a model of the forces acting upon an object. This model is called a free body diagram. A free body diagram represents an object with a dot and arrows pointing outward from the point with varying lengths and directions to represent the magnitude and directions of the forces.
The push force is the applied force from the tennis racket to the tennis ball. Its force arrow is longer than the others because it is the greatest in magnitude, and this states that the motion is in the direction of the push force. However, the force of gravity is also present, which causes the ball to move downward in a parabolic arc.
Although minimal, a drag force is also acting upon the ball. This is due to its movement through the air as it collides with air molecules, minutely slowing the ball down. Drag force is present when an object is moving through a fluid, which causes it to slow down.
This scenario is a splendid example of Newton's third law of motion. The third law states that for every action, there is an equal in magnitude and opposite in direction reaction. These pairs of forces are called action-reaction pairs.
In our tennis situation, the amount of force applied on the tennis ball from the tennis racket is equal in magnitude to the force applied from the ball onto the tennis racket. However, both forces are in opposite directions.
If so, then why is the effect of the force on the racket less than the effect of the force on the tennis ball if the forces are equal in magnitude?
That is because the masses of the two objects are different. Because the mass of the tennis ball is much less than the mass of the tennis racket, the tennis ball has a greater change in motion than the racket. If the same force is applied to two different objects of different masses, then the effects on each object will vary. This is further supported by the fact that the action-reaction forces are acting on separate systems.
The tennis racket acts upon the tennis ball, and on the flip side, the tennis ball acts upon the tennis racket with an equal and opposite force. This is why the forces do not cancel each other out. Another especially important concept is to account for is that Newton's third law requires two or more objects, as shown in the example.
To examine the net force acting on the tennis ball, we can utilize Newton's second law. This law states that the net force is equivalent to the product of mass times acceleration. From this equation, we can infer that as the tennis racket applies a greater force to the tennis ball, its acceleration will increase. This means there is a greater net force, since our mass is constant and not decreasing. Additionally, Newton's second law states that acceleration is inversely proportional to mass, and net force is directly proportional to acceleration. These are the proportionality statements of Newton's second law.
Force is the sum of all forces acting upon an object. We can decide which directions are our positive directions, and based on that, calculate the net force.
There is a common confusion between weight and mass. They are related but not the same. Mass equals the amount of matter that makes up an object, whereas weight is the product of mass times gravitational field strength.
Is there a way to calculate the trajectory of the tennis ball?
Yes, we can apply the concepts of projectile motion. The basic concept of projectile motion is that motion has two components, a component in the x direction and a component in the y direction. Neither of these components relates to each other. They are independent of each other. The x component is the horizontal portion of the resultant vector. Similarly, the y component is the vertical portion of the resultant vector. The resultant vector is the sum of two or more vectors.
If the angle between two vectors is equal to 90 degrees, you can use the Pythagorean theorem. If the angle between the two vectors is 180 degrees, then simply add both vectors, making one vector in the positive direction and one in the negative direction. However, if the angle between the two vectors is neither 90 degrees nor 180 degrees, then you encounter trigonometry. These are the math concepts of sine and cosine. These concepts are derived from a circle named the unit circle. The unit circle has a radius of 1, and from the circle, mathematicians derive the common trigonometric functions of sine, cosine, tangent, cotangent, secant, and cosecant.
Sine, if we are considering the angle measured from the horizontal, is the height of the triangle. To use sine, you take the hypotenuse and multiply it by the sine of the angle. Calculating this gives you the y component if the angle is relative to the horizontal.
Cosine, if we are considering the angle measured from the horizontal, is the length of the triangle. To use cosine, you take the hypotenuse and multiply it by the cosine of the angle. Calculating this gives you the x component if the angle is relative to the horizontal.
Angle is relative to the vertical, then flip the sine and cosine for the x and y components.
If you want to use the x and y components in your calculations for further solving, utilize the kinematics equations with appropriate variables.
You guys have been saying vector many times. What is a vector?
A vector is a quantity with both magnitude and direction. For example, velocity, force, and displacement are all vector quantities. However, a scalar just includes magnitude. For example, speed, distance, and mass are all scalar quantities.
Wow, that was a lot to cover in such a simple example of a tennis racket hitting a tennis ball. From this, we get the understanding that forces are widespread throughout the universe. They are multiplex and govern the way that everyday life is lived.
Have you ever wondered how a rocket propels itself through the void of space?
Rockets are propelled with thrust force.
Thrust occurs when a rocket ejects gas backward out of the thruster, causing the gas to push back on the thrusters, propelling the rocket forward. This is an example of Newton's third law pairs.
Due to the high speed of the rocket, there's a considerable drag force in the opposite direction of the rocket's motion, which slows it down.
Wait, how does a rocket fall back to Earth after it has completed its journey?
When a rocket is progressing through its fall back down to Earth, the only force acting upon the rocket is gravity and some drag. As the rocket accelerates into our planet's atmosphere, it reaches a point where it can no longer accelerate as the force of gravity and drag forces are balanced, meaning net force equals 0. This condition is known as terminal velocity.
When the rocket is in terminal velocity, it is also in dynamic equilibrium. This is when the net forces are balanced, but the object remains in motion, as demonstrated in this example. On the other hand, static equilibrium is when an object is at rest and remains at rest while the net force is still 0.
For the object achieves terminal velocity, it is in freefall. Freefall is when the only force acting on an object is gravity.
How do airplanes calculate their displacement accurately, considering their change in direction and angle, including their distances?
We can use a method called vector addition and subtraction. There are two methods to calculate the sum or difference of vectors. These are the graphical and analytical methods.
In the graphical method, you utilize a Cartesian plane and graph the vectors according to their direction and magnitude. The second vector must be drawn using a technique called tip to tail. This demonstrates that the second vector's start is the first's end. Finally, you draw in the hypotenuse, also known as the resultant vector. The magnitude of this line, measured with a ruler, is the magnitude of the sum of the vectors. The angle of the resultant vector, measured with a protractor, is the angle at which the object travels.
An alternative way to calculate the resultant vector is by applying the analytical method. When using this method, it is useful to create a model of what the graph would look like. Find the measurements of the triangle we can use sine and cosine. However, to find the angle of the resultant vector, you can use a formula called inverse tangent. This formula will give the angle of the triangle. However, you must be cautious when dealing with which axis the angle is relative to. Depending on which axis the angle is measured by, the magnitude of the resultant vector will also change.
How do people move around? Like, what causes them to move? Is there a push force from the foot to the ground, or is there another reason?
There's a much different reason. It is the force of friction that allows humans to move with each step. More specifically, it is static friction. Static friction is present when there is a push or pull force, but it is not strong enough to overcome the force of friction. A property of static friction is that it only pushes as hard as it needs to balance the opposing force, making the net force zero. This type of friction is less than or equal to its maximum, which is bound by the product of the normal force and the coefficient of static friction. The coefficient of friction in general describes how hard it is for the surfaces to move against each other. These values are generally less than 1, with 1 having a large amount of friction and 0 being frictionless. This is represented as mu.
There's another type of friction called kinetic friction. As depicted by the name, it is the force of friction acting upon a moving object. Kinetic friction is always equal to the product of normal force and the coefficient of kinetic friction. All types of friction act in the opposing direction of motion or attempted motion. This slows down the motion of the object.
An object at rest demonstrates Newton's first law of motion, which states that an object in motion will remain in motion and an object at rest will remain at rest unless acted upon by an unbalanced net force. This is also known as inertia, which describes the tendency of an object to remain in its current state of being.
Although intuitively, an object in motion should constantly remain in motion due to Newton's first law, the motion of the object is slowed by the force of friction.
We have examined forces on a horizontal plane and an object soaring through the air. But what happens when objects are on inclined planes?
Inclined planes are similar but have a number of differences. The main difference is that an inclined plane is at an angle compared to the horizontal planes. This creates several differences.
First, on a horizontal plane, the normal force goes upward, but because of our change in the angle of the plane, the normal force is perpendicular to the ramp, which is inclined. Another difference is that the y component of gravity balances normal force, instead of gravity balancing the normal force on a horizontal plane. This is because the gravitational force continues to pull the object to the center of the Earth despite the incline. Moreover, the x component of gravity counteracts the force of friction, whereas in the horizontal plane, the push or pull force opposes the force of friction.
To calculate the x and y components of the force of gravity, we utilize trigonometric functions discussed earlier. When the angles are relative to the horizontal, sine is the height, or y component, and cosine is the length, or x component. When relative to the vertical, these are switched. For inclined planes, the angles are relative to the vertical. To calculate the y component of gravity, which counteracts the normal force, multiply the gravitational force by the cosine of theta, where theta is the same angle as the angle of the incline. In most problems, the y component of gravity and normal force are completely balanced.
Calculate the x component of gravity, which counteracts the force of friction, multiply the gravitational force by the sine of theta. Gravitational force in the x direction is the most common reason for motion on the incline.
If you are required to calculate the net force of an object on an inclined plane, the difference of the force of friction and the x component of the force of gravity equals to the net force in the x direction. To find the net force of the y direction, it is equal to the difference between the normal force and the y component of the force of gravity. However, in most common scenarios, the y component of gravity and normal force are completely balanced, resulting in zero net force in the y direction.
I find grandfather clocks very interesting. Can you describe their motion using physics calculations?
The concepts that describe this motion are called simple harmonic motion. This includes the variables of frequency and period. However, it's important to understand what an oscillation is before we define period and frequency.
An oscillation is when an object moves back and forth in a repeated manner between two different positions. This is also an example of deformation, when an object undergoes a displacement from its equilibrium state due to the application of force. If each oscillation takes the same amount of time, then the motion is periodic. This type of motion is commonly seen in springs and pendulums.
Period is defined as the amount of time it takes to complete one oscillation. Period is represented by capital T, and its unit is seconds.
Frequency is the number of oscillations per unit of time. This variable is represented by lowercase f, and its unit is a hertz. Frequency is equal to 1 over the period.
Before we can calculate the period, we must understand the concept of springs. After a spring has been compressed, it moves back and forth between two positions. The midpoint of these two positions is the equilibrium position of the spring, and the velocity is equal to 0 at this instant. The equation to calculate the restoring force of the spring is Fs equals negative k multiplied by delta x. K represents the spring constant, and the larger k is, the stiffer the spring is. X represents the displacement of the spring. Finally, Fs represents the restoring force of the spring.
This formula is known as Hooke's law. It also states that the deformation is directly proportional to the force. Additionally, the restorative force is directly proportional to the displacement. Now, we can finally calculate the period using the equation T is equal to 2 pi square root m over k, where T is the period, m is the mass, k is the spring constant. As a note, motion is the result of gravity, inertia, and spring tension. Equilibrium occurs when the spring force is equal to the force of gravity.
To calculate the period of a pendulum, as in a grandfather clock, we need to understand a few important concepts. It is important to understand that a pendulum only experiences simple harmonic motion when the angle is less than 15 and the string has negligible mass. Any theta over 15 degrees is not considered simple harmonic motion. To calculate the period of a pendulum, use the following equation. T equals 2 pi square root L under G. L represents the length of the string or rope of the pendulum, and G represents the gravitational strength.
The force on a pendulum is represented by the equation F is equal to negative mg sine theta, where m is the mass and g is the gravitational strength.
And that's all we have for you. We have faced a variety of topics detailing the nature of physics in our lives.
From things like tennis to springs, it's thrilling to learn about our own world, which is often neglected.
We hope you enjoyed this crash course on the principles of forces and motion.